Hello, today we'll talk about compressibility effects in terms of turbulence, not necessarily in the flow. So this is where the turbulence itself has some compressibility. And let's look at some introductory comments. So for compressibility effects, when they're important, we'll need, of course, equations for conservation of energy, unlike the incompressible formulations, and an equation of state. It's a gas law. Normal one is ideal gas, but we don't have real gas or chemically reacting flows. Now, typically, Reynolds averaging will give rise to the Reynolds stress tensors. And we would expect similar averages will lead to, say, turbulent heat flux vectors, which is a new modeling problem that we would see in compressible flows, unlike incompressible formulations. And we would certainly expect that new compressible-related correlations will appear through the equations of motion. So that's an actual difficulty. So in this class and the upcoming one on the most typical closures, we'll just look at some observations of common closures and also some important or well-known closures. So in this class, we'll look at the first right here and mainly look at the physics and sort of common observations. So for compressible flows, this is one in which, at least for a turbulence modeling viewpoint, there's significant density changes which occur even when pressure changes might be small. And that does include low-speed flow with large heat transfer. And we might have high-speed flows meeting these models with perhaps exception for combusting flows. It's maybe the most obvious example. And of course, there's compressibility will have a small effect on the turbulent eddies in wall-bounded flows. At least very near the wall. Why? Because near the wall, the flow is slower. And that's on the turbulent eddies. And typically Mach numbers above 5 to 8 in that region don't experience compressibility in the turbulence, and higher Mach numbers will. But certainly across shock waves, turbulence and compressibility are very important. And perhaps at subsonic speeds, the compressibility of eddies are usually unimportant, especially for boundary layers, provided that the temperature at the wall, the temperature at the edge of the boundary layer is less than 6. Now there's the Morkovin hypothesis published in 1962, and it's stated that the effect of the density fluctuations on the turbulence will be small, provided they remain relatively small to the mean density changes. So this is a major simplification which is made in almost all classic and well-used turbulence models. because it means that, in practice, we only need to account for the non-uniform mean density. And that means there's some limitations when we make an assumption, like all assumptions, including the Morkovin hypothesis, even at non-hypersonic Mach numbers, meaning like Mach numbers roughly 5 to 8 over slender high-speed bodies. And what are some examples of those? Well, one example would mean that it's not useful for particular flows with significant heat transfer or for flows of combustion. Why? Because rho prime over rho bar is large. Another example might be density for these fluctuations would mean that, say, in free shear flows, the models based on Morkovin's hypothesis won't be able to predict the measured reduction in spreading rate with increasing Mach number for compressible mixing layers. And this was discussed and shown in a famous paper by Papamoushu and Roshko. And I think this was done at Caltech in 1988. Roshko was the professor and advisor, and Papamoushu was a student. Another example is where perhaps levels of rho prime over rho bar for boundary layers at Mach 5 will be comparable to the level found, say, in mixing layer at Mach 1. Two shear type flows when one is bounded. The mixing layer structure for these types of cases will increase, that is the mixing, at higher speed flows. And so on dimensional grounds, we might expect that the velocity determinant boundary layer will depend on, say, basic fluid properties like Prandtl number and specific ratio of heat. So generally there's three particular dimensionless groupings that we would examine. One, of course, is y plus, and that's the sublayered scale distance. The second is a dimensionless heat transfer, Q plus, and the third, which we talked about before in this class, is the turbulent Mach number. Here the W denotes wall, Q is heat flux, Cp is specific heat at constant pressure, and T is temperature, and A, or C, is the speed of sound. So based on the mixing length model, which we talked about previously in the class, way back based on the Prandtl mixing length model, and also assuming that, in analogy to the compressible case, we might write that partial U partial Y in, say, a boundary layer or shear type flow goes as the root of tau W over rho divided by a constant kappa times Y. Here, density is a function of Y, which is the distance from the wall. Now, Van Driest in 1951 argued that by rescaling the velocity, we might be able to write an equation like this, where U star over U tau is 1 over A times sine of 2A squared times U over U tau minus B all over the root of B squared plus 4A squared half plus B all over square root of B squared plus 4A squared. Closes the equation. And here A and B are just functions of QW and turbulent Mach number, heat transfer and turbulent Mach number. And so we will look at this equation later in more detail. Now, based on this, we can write, just like the incompressible case, the law of the wall holds, and 1 over kappa, a constant, times the natural log of y plus c. So really, 8.4 is a form of the compressible law of the wall, as long as U star retall kind of goes like this. Now, it happens to be the correlations and measurements show that both K, or kappa, and C are nearly the same for incompressible flows. And here, C is really a function of MT. And QW plus Y, because it includes density and viscosity effects in the viscous wall region. Compressible law of the wall, 8.4, correlates experimental data for adiabatic walls really well. Unfortunately, it's less accurate for non-adiabatic walls. And it's even less accurate for non-adiabatic walls where the walls are very, very, very cold, and then C is also going to very strongly more strongly with, say, QW. There's also variations of, say, temperature with these parameters that can be deduced for very low speed flows. Unfortunately, the use of compressible law is relatively sensitive to pressure gradient. So it's really well developed, the law of the wall, and composite profiles for flows with pressure gradient. Compressible law of the wall has much more trouble when there's strong pressure gradients with matching measurement data. And based on this, we might find that there might be simple free shear flows are actually more difficult to model than the wall-bounded flows because, of course, of this different scaling with onset of Mach number that we noted earlier. So based on these basic physical considerations, in the next lecture, we're going to talk about the basic models, review Favre averaged equations, and then we'll look at different closures for the different correlations.